Assalamualaikum and a very good day, class. Today we shall learn about Chapter 2, Metallics Material. Metallics Material consists of 14 hours lecture. In this chapter, we shall learn about solidification of pure metal and alloys, phase diagram, microstructures development and microconstituent of phases, iron-iron carbide system, microstructure development and microconstituent of phases, and ferrous and non-ferrous metal. Let us start with 2.1, Solidification of pure metal and alloy. In this subchapter, we shall learn about all the terminology that we shall use in this subchapter. What is solution and the metal type solution, type of solid solution, which we have two, substitutional solution and interstitial solid solution, the solubility limit, and solidification. We shall also learn about cooling curve, which is the cooling curve of pure metal, cooling curve of alloy, development of phase diagram, and cooling curve for binary isomorphous. Let us start by watching this video.
Oh, I can't finish it fast, and it is melting.
Oh yes, mine is melting too.
Why is this melting?
You know, everything is made of molecules. When you heat molecules, they start moving faster.
Then what happens?
Let's enter the world of molecules to see this. You know, these molecules in solid are tightly packed and they don't go out, but they're not fixed. They keep moving. They come near to each other and then again go away, like saying, I'm your friend, and no, I'm not your friend.
Like you and me.
Yes, but when it gets hot, they start moving away from each other. And you know, when molecules are far from each other, what happens?
Yes, matter becomes liquid.
Yes, it is also called melting.
Melting. When molecules in solid becomes apart, it turns into.
Just wait.
After some time,
Oh, it has turned into solid again.
Yes, the molecules again become slow and come closer to each other, and it becomes ice and solid. It is also called freezing.
So, as a conclusion, when an atom gets closer to each other, it becomes solid. When an atom gets far away from each other, it becomes liquid. The learning objective of this subchapter is students should be able to understand what happened or what is the phase transformation during the solidification process. Solidification process is a process where liquid turn to solid or solid turn to liquid, and what happened in between. And differentiate between the cooling curve of pure metal and alloy. Here are some terminology that are important in this subchapter. The first one is solvent. Solvent is an element or compound that are present in greater amount, meaning to say, in an element, if the elements are in a great amount or in high amount, it is called a solvent. If it is in a lesser amount or lower amount, it is called a solute. And when solvent and solute combine together, they will create a solution. For example, we have solute here. For example, we have sugar and solvent water. So when the solute, which is in a smaller amount, are added to solvent, which is in higher amount, we will create a solution. Please try and answer this question. If a syrup cordial, which is actually syrup plus water, are added together, which one is solvent, which one is solution, and which one is solute? Or number 2, prawn fritter, or formerly known as cucuk udang in Malay. It consists of prawn and flour mixture. Which one is the solute? Give some example of the solution that you know. Another terminology is solubility. Solubility is the degree or how much to which the two components can mix together. And we also have solubility limit. This is the maximum concentration of solute that can be added without forming a new phases. For example, in the solubility limit, if you add a sugar in the water, it will create a syrup. But if you add too many sugar, what happens is you can see the additional sugar separated from the water. So it can say that it has reached over the solubility limit. Now, let us learn about the component in metal. Take a look at this example. The element or compound which are mixed initially, which is aluminium and copper. You can see there are two distinctive or different material here. Beta happen in the lighter phase and alpha happen in darker phase. So the aluminium copper alloy are differentiated by these two phases that can be seen distinctively together. When two components are combined together, they can either remain separated or combine to form a single phase, which is referred as a solution. For example, we have alcohol and water. Both of these are completely soluble. You cannot differentiate which one is alcohol and which one is water once it is completely soluble. And then the second one is hot chocolate and powder mixed soluble. So the hot chocolate powder limited extent to the water. If you add it too much, you can see the hot chocolate powder on top of the water. And lastly, we have oil and vinegar, which is insoluble. So oil and vinegar do not mix with each other. In metal, most metal are combined to form alloy in order to impart special characteristic. An alloy is a combination of two or more elements. Usually what we add is the impurity atom of at least one of the metal. The addition of impurity atom to the metal will result in the formation of solid solution. So let's say you have an iron, okay, or we know as besi. So to improve the properties of the iron, we add some alloying element. For example, we add carbon to the iron to increase the hardness. So the carbon is actually the impurity atom that are added. So which one of these two, carbon and also ferrum or iron, is the solute? Which one is the solvent? Let's say we added the carbon to the iron. So meaning to say the carbon is the solute and the iron is the solvent. These two to create a solid, and this solid must become hard to make it a solution. Okay, that is why it is called as solid solution. Okay, a solid solution is a solid state solution of one or more solute in solvent. For example, we have steel and cast iron, brass and bronze, and other types of alloy. Here are the characteristics of the solid solution. It must form when the solid atoms are added to the host material. But when the solid are added to the solvent, the crystal structures, okay, as we have learned before, we have FCC, BCC, and SC. When you add the solute, the crystal structure will be maintained. They will not become another type of structure, and no new structure shall be formed. And it shall be compositely homogeneous. Okay, what does it mean by compositely homogeneous? It does not transform to another material. Okay, for example, when you add something to aluminium, when you check, okay, it still have the same structure. Okay, and it's still an aluminium. It does not transform to another types of material. Okay, for example, when you mix nickel and copper. So when we say the solvent is nickel, we know that nickel is in the higher amount, and solute copper is in the lower amount. So you see here, okay, nickel is represented in the white, okay, the white sphere, and copper in the blue sphere. So you see that the amount of copper added, okay, is less than the amount of nickel. Okay. Type of solid solution. We have two types. The first one is substitutional solid solution. We substitute, okay, the atom, okay, that's supposedly in this position. We substitute it with another atom, which is what we call as solute lah. Okay, so solute ni is added to the another solvent, and it's replace, okay, it replace, okay, the atom in one of the position. And another one, we call it as interstitial solid solution. This one, okay, it does not replace any of the atom, but it is being immersed, okay, it being immersed, it is so small that it can take the place in other area outside the atom. So that is the difference between substitutional and interstitial solid solution. So in order for us to know whether it is a substitutional solid solution, we must apply the home rotary rules. In this rule, we have 4 rules. The first one is the atomic radius. In order for us to choose the material to be added, okay, we have first take a look at the atomic radius. The atomic radius must be less than 15% or more than 15% different in the atomic radius. Meaning to say, the maximum allowable limit of the size is only 15%. It must be 15% larger or 15% less. Then only it can substitute, okay, it can replace the atom that you want to replace. Okay, and then number 2, the crystal structure must be the same. For example, if the material you want to be add is BCC, then the material to be added must be also BCC and vice versa. Okay. The third one is it must have similar electronegativity or very small difference. And the fourth one is it must have same valence electron. Okay, look at this example. Okay, when the solvent is added to the when the solute is added to the solvent, okay, the size is quite the same, okay, so that's why it can be added. That one is the atomic radius, and the crystal structure is also the same. Electronegativity and valence electron is also the same. Okay, note that not all alloy are fit to this system. Okay. Example. Let us take a look at the example. Okay. The first one is copper-nickel system. In this system, both metals are completely soluble in each other. Why? Because all four requirements are being fulfilled. So this is what we call as complete solid solution. So first look at rule number 1, atomic radius. The atomic radius for copper is 0.28 and the atomic radius for nickel is 0.25. So when we calculate, we know that the percentage of changes in the radius is only 2.3, less than 15%. So rule number 1, check. And then rule number 2, look at the crystal structure. Both have FCC crystal structure. So check. Number 3, the electronegativity. The amount of electronegativity for copper is 1.9 and for nickel is 1.8. Quite similar, less than 10% value of changes. So check. And lastly, let us take a look at the valence electron. Okay, the electron that is on the outside of the shell. Okay, at the outer shell, which is +2 and +2. So we know that they are completely soluble because all of the rules are being satisfied. Okay, then let us take a look at another example of copper and argentum. This one, they are partially soluble or limited solid solution. Why? Let us take a look. First, look at the atomic radius. The difference is less than 15%. Okay, check. The second one is both have FCC crystal structure. Check. And the third one is the electronegativity less than 10%, check, but look at the valence electron. One have 2 plus and another one have 1 plus. So this rule does not comply. That is why this type of solid solution, this type of material have only limited solid solution. Okay, imagine when you put a sugar inside a water, so when it reaches certain limit, okay, the sugar will not dissolve in the water. So this is the example. So what happens if all four rules are not complied? Then we call it as no solid solution. Okay, let us move to another type of solid solution, which is interstitial solid solution. Interstitial solid solution can only exist when first, an impurity atom fill the void in the solvent atom lattice. So we have the void or the blank area over here. If the impurity atom can fit into this area, then it is actually can comply with the interstitial solid solution. And it can intersize, okay, it can penetrate, immerse among the host atom. The atomic diameter of an interstitial purity must be smaller than the host atom. As you can see, the blue one over here, okay, which is the carbon, is much more smaller than the iron. And the maximum allowable concentration is less than 10%. Okay, so that is all class for today solid solution class for chapter 2.1.1. Thank you, class, for your attention.